Okay, so we have our two populations, the women that worked with glycol ethers, the pregnant women who did not. And let's think about possible hypotheses, right? If you got, at the end of the day, right, proportions are just numbers. And so if I have two unknown numbers, what are the possibilities of how they relate to each other? Well, either one number is less than the other, one number is greater than the other, or they're equal. And so that's what we have here. This is the context. We have two population proportions. We denote them with P1 and P2. And here's our tongue twister, possible hypotheses. The proportions are equal. The first is, if you're looking at the alternative, the first is less than the second, or the first is greater than the second. That's it, okay? Now, what are our requirements? Well, of course, we need simple random samples. They need to be independent, and they must be large enough to use the normal distribution, right? Now, since we have two different populations and two different samples, we have to check that, right, we have that greater than or equal to 5 requirement met for both. Now, what does the standardized test statistic become? Well, we're looking at the difference, P1 hat minus P2 hat. So that P hat, right, is our sample proportion. And we have two different samples, hence P1 and P2, P1 hat, P2 hat. And when we go through and do this, we're going to assume that P1 minus P2 is 0, okay? Again, think about the null hypothesis, right? We have them equal. And then divided by this rather ominous looking denominator, where P bar and Q bar are defined as follows. So P bar, essentially you take the number of successes from both samples and you combine them. Think of it as like a super sample. You put the two samples together, you get this P bar, and then Q bar, of course, is just 1 minus P bar. To be honest with you, this is something that we'll use a calculator for, but you still need to know that that's the formula, okay? All right, so let's come back to our motivation problem here. We want to start by defining our P's. So let's let P1 be the proportion of women working with glycol ethers who suffered a miscarriage. And let P2 be the proportion of women women not working with glycol ethers who suffered a miscarriage. Okay. Now we're ready to write a claim. Okay. And so my claim, well, let's see where that comes. Test the claim that the miscarriage rate is greater for women who are exposed to glycol ethers. So that tells me that P1 is greater than P2. Okay. Well, now we're back into that same routine as our previous hypothesis test, right? The structure is the same. We have a claim, we mathematicized it, we want to place it in the appropriate hypothesis. Well, there's no equality here, so the claim goes in the alternative. which means the null be less than or equal. Or again, you know, for simplicity's sake, you can just think of it as equal, okay? And then we've got, whoops, wrong color. It's a nice color though. We have alpha at 0.01. We have right-tailed. Okay. And so now, notice that we've met the normal distribution requirement, right? We have more than 5, quote, successes and failures for each, okay? And so right-tailed, that area there, 0.01. This is my fail to reject region, okay? And here's my critical Z. And so for a right-tailed test, right, you can get that critical Z with an inverse norm computation. Of course, these should start to be familiar, right? So 2.326. All right. And now we want to go get our standardized test statistic. So if I want to do this by hand, then I have P1 hat is equal to, well, 30 worked with glycol ethers, 10 had miscarriages. So 10/30ths. My P2 hat would be 120 over 750. And then my P bar, you know what, let's do our N's first. N1 is 30. N2 is 750. And then my P bar would be, and here's where we combine them, right? 10 plus 120 all over 30 plus 750. So 130 over 780. And then Q bar would be 1 minus 130 over 780, which would be equal to, well, 650 over 780. So we have all the pieces to this lovely formula here, okay? And so you plug them in, you go to work. Or how about we do this? How about we come over to our good old calculator and we go over to stat tests, and hey, what do you know? Right down there is 2 prop Z test. Hey, so X1, those are my miscarriages among those who worked with glycol ethers. Well, there were 10. And how many were in that group total? 30. And then how many miscarriages among the non-glycol ether group? Well, there were 120. And how many pregnant women were in that group total? Well, 750. Our null is that P1 is greater than P2. So now we calculate. There we go. 2.498. So I'm just going to say 2 prop Z test gives me a Z of 2.498. And where is that 2.498? Well, it's in the rejection region, right? And so we are going to reject the null. Where was our claim? Well, our claim was the alternative. So at alpha equals 0.01, there is sufficient evidence to support the claim that the miscarriage rate is higher among the pregnant women who worked with glycol ethers. Okay, well, let's put this into a practical perspective here. Remember that at the end of the day, statistics is used to inform decisions. So what decision might this be used to inform? Well, yeah, you're probably going to have a class action lawsuit on your hands if you're IBM, right? And you'll cite this research, very basic test, right? Maybe we'll charge, I don't know, a couple $1,000 for this 10-minute analysis as consultants. And they'll say, look, it's clear. Evidence shows that their miscarriage rate is higher. Now, if you're an attorney for IBM, what would you be looking for here? Well, you'd be looking, because you're not going to argue with what we just did. These results are the results. It is what it is. You know, there's this alpha of 0.01. Are you going to argue that, yeah, well, you know what, maybe this is just that 1% chance that these results are wrong? It doesn't seem like a very strong argument, especially since, if you think about it, this 2.498 is out here somewhere. So we could even move this critical Z farther and show that we're actually good at much more significance than just 0.01. So that's not a very good idea. Well, maybe there's something else going on. Maybe these women all decided to drink the glycol ether. Maybe they were like the Manhattan Project when we were building the atomic bomb, and booze was just really hard to get in New Mexico on the base. And so you had to take your lab alcohol and mix drinks with it. True story. They really did that. Maybe these women were in that spirit and they decided, hey, let's see if we can mix some drinks with this. Or maybe there was some other confounding variable. Maybe they were all involved in really dangerous side behavior and belonged to the same club. I don't know. I'm clearly reaching. But the point is, the defense attorney is not going to necessarily take issue with this. They're going to have to look for another explanation. Okay. All right. Let's look at the Salk vaccine. See how this plays out with this type of hypothesis testing. In initial tests of the Salk vaccine, 33 of 200,000 vaccinated children later developed polio. Of 200,000 children vaccinated with a placebo, 115 later developed polio. At 0.01 significance, test the claim that the Salk vaccine is effective in lowering the polio rate. Well, we need to mathematicize that. Effective in lowering the polio rate. In other words, the proportion of people vaccinated who got polio should be less than the proportion of people not vaccinated who got polio. So let's again define our proportions. Let P1 be the proportion of vaccinated children who later got polio. And let P2 be the proportion of vaccinated children, I'm sorry, of non-vaccinated children who later developed polio. Okay. So it's effective if this first proportion is smaller than the second. That's my claim. P1 is less than P2. Okay? So I'm not sure if this was up and showing. Okay? So we've got our two populations here. Now, let's hypothesize. Let's place these in the appropriate hypotheses. H0 and HA. My claim is in HA because it doesn't have equality. And so my null will be greater than or equal to. And again, we just think of that as equal. Okay. All right, well, my alpha is 0.01. This is left-tailed. By the way, could I have done this right-tailed? Could I have also said if you're not vaccinated, the proportion is higher? Absolutely. That's an equivalent test, logically the same. Right? If A is less than B, then B is greater than A. I just set this up as left-tailed. So let's sketch out our distribution. Here is my alpha, way out in this tail. And we know by now, just from experience, what that actually is. And so here we're going to do our fail to reject. Okay, and now let's go get our standardized test statistic. So 2 prop Z test is going to give me a Z of, so let's come over here and look at our calculator. Stat tests number 6. So let's clear out what we had before. So the initial X1, so those that were vaccinated, we had 33 of those. Okay, so 33 of the 200,000. So X1 is 33, N1 is 200,000. Now X2, the non-vaccinated, it's 115 who got polio out of 200,000. And then we're saying P1 is less than P2. -6 point, and actually I quit reading after that because that's so far in the rejection region, but let's see, -6.742. Okay. All right. And so reject HO. So at alpha equals 0.01, there is sufficient evidence to support the claim that the polio rate is lower for those who are vaccinated. Okay. Hey, let's try one more. And maybe you guys try this one. Just see if it works, okay? See how you do. So I'm gonna encourage you to pause it and go ahead and work out this problem. Okay, so here's my setup. I define P1 as the proportion of boys who work. P2 is the proportion of girls who work. By the way, sometimes it's even nice, if you want, you could call it like PB or maybe PG for girls. You can assign more meaningful subscripts than just 1 and 2, but I'm gonna stick with 1 and 2. All right, so let's see what we got. We have an alpha. Are we at 0.01 still? Oh, it doesn't say. Well, if it doesn't say, we're gonna default to 0.01. And so I know that my critical, because I've done just a few of these, is 2.326. Here's my fail to reject region. And then let's go get the 2-prop z-test. Okay, so let me show you the calculator here. And so in our 2-prop z-test, our x1, let's go back to our sample. We have 5,000 boys, 1,200 worked. So 1,200 we had 5,000 boys total. For girls, we have 660 who worked and 3,000. And we're saying the proportion of boys is greater. All right, 2.050. Whoops, 2.050. Well, that is in the fail to reject region. So alpha equals 0.01. There is insufficient evidence to support the claim that a greater proportion of boys work than girls. All right, guys. So spend some time working back through this. Again, right? You want to make sure that you've got all the pieces. So, you've defined your P's, your population proportions. You've set up your 2 hypotheses. You've got the standard, as in this distribution with your critical. You've identified what the test statistic is, the decision, and then finally, the most important part, the statement, okay? All right. So I would encourage you guys to go back and look at this, review it, and when we come back together, we will talk about hypothesis testing for 2 different means, claims about means. And so until then,